tell me to say that one, but he has some really cool music on SoundCloud that I would really encourage everyone to check out. Anyway, without further ado, let's get started with the second half of the session with Ken Wheeler, everybody.
Hey everybody. I'm Ken. That's Ken_Wheeler on Twitter, if you want to read a bunch of garbage. And today, I'm here to talk about audio DSP. And what DSP is digital signal processing, which is actually wild because it gets used in a lot of different places. My background is audio. I used to be a rapper and producer. I still am. I just do this programming thing for fun. But yeah, this is the context. And then like when I started writing this, I was like, oh wow, that's not just for making beats. That's cool. So audio processing and synthesis is one of the applications, right? They do a lot of it in things like statistics, medical stuff, image, video processing, all kinds of things, anywhere there's a signal. But I don't know anything about any of that. So today we're going to talk about audio, and we are going to build a synth. Or let's talk about how you would build a synth. So I've already built a synth, but we'll get there. So the first part of that, right, I guess the most granular level where you would start is, how do you create sound digitally, right? Like if you're going to create sound in an analog way, there's two options, right? You could like play a guitar, or if you wanted to make like electronic music, like synthesis, you'd be like an electrical engineer, and you'd work that out. But I'm not an electrical engineer, I'm a programmer, so we're going to make it digitally. And the way that you do that is you start with an array. Right? That's where we're going to get going here. And in order to fill that array, we need to know some things. The first thing is the sample rate, right? And what that is that's like the number of data points of audio per second. All right? This is like your granularity of your signal. I'm sure you've seen like on like the cover of your CD player, or in like a Winamp tab somewhere, like this 44 100 hertz. And you're like, oh, okay, yeah, that's a sample rate. That's great. Yeah, good music. But what that means is there's 44,100 samples per second, which make up your audio signal. The second thing that this is like a waveform going here, and each one of these divisions is a sample, right? So the second thing you need to know is your buffer size, and that's the number of samples that you're sending to the sound card at a given time, right? So if you make too small of a buffer size, if you've ever worked in audio, you've probably seen this, like you make the buffer size smaller and it's like, the computer can't fill the buffers fast enough and process them fast enough, right? So you have to give enough buffer size so that you have a little leeway. If a buffer is too big, you have the opposite problem. If you're synthesizing, right, and you like press the key on like a MIDI keyboard, you're gonna get a delay. And then, you can't even do anything because it's like out of sync with your finger hitting. So your buffer size should be just right. So back to our array. Let's operate under an assumption that, we have a 44 100 sample rate, pretty standard, and a buffer size of 1024, right? And then let's say this square represents a single sample. Each buffer is going to be this many, which is kind of bananas from a data perspective. And then there's 43.06 of these per second that are getting sent out. Not the square, the collection of squares, which is a lot to be streaming out. It's kind of wild. So say we have this array filled with this data. How using Reason, how do we play that natively, right? The answer is this thing called port audio that there just happen to be OCaml bindings for. What port audio is it's like a cross-platform audio I/O library where you can like select a sound card or output source or input source for that matter, and you can write these buffers to it. Typically when I have been making music, right, like that's not how you're doing it, right? You have like a audio workstation and a synth and all that stuff like that, but this is about as low level as it's going to get, like just throwing numbers at the sound card. And port audio is what lets you do that. So to actually use this, right, it's not too bad. Can you see my cursor there? Okay. So we initialize port audio, and then we can grab like the default output device, get some device info, and then we're going to set up these output options here, right? So we're going to say 2 channels, right, which is stereo. We have our device ID, right, our sample format, and our latency, right? You can kind of pick like a default latency, and then you open a stream. As far as what you're actually sending to it, what you're writing to it, you use big array, right? So we create this buffer, this array buffer, and it kind of just exists, and we're just writing it to port audio here. We're just writing it to the stream, and then on each iteration of this loop, we're just kind of overwriting it. We're just filling that array buffer with our data based upon a variety of parameters. So filling our buffers, right? Like now we're writing signal to the sound card, right? How do we turn this into sounds that are pretty? Actually filling up the buffer, we want to, up here we're gonna set a time, right, which is gonna be 0. And then we calculate our delta, and our delta is going to be the amount based upon the sample rate that we're incrementing as we traverse through. In here, if it's like bigger than float can be, we reset it back. We pass the time into, what would be, this is just like kind of like a mock get data function, right, where all of our synthesis is going to occur. And then, for each iteration, we're going to increment our time and then overwrite in the array buffer. So, what do we put in there? And that is waveforms. If you've done more college level math than me or done any music production, you're probably familiar with these rascals. So here's some basic waveforms that you'll see when doing synthesis. A sine wave, that's like your 808, like the square wave. If you listen to a lot of like British D&B, you might get onto that. Sawtooth, that's like Skrillex stuff all day. Generally speaking. And these get created by things called oscillators. It spins around and generates our signal. So oscillators emit waveform values over time, right? Your frequency, right, which is like your pitch or your note, do, re, mi, what have you, that determines how fast it oscillates. Right, so a higher frequency, like if we were like, boop, right, this is going to be this guy right here, like super tight waves. Down here, it's like, sorry, sound effects, low fidelity audio. You're going to have a longer wavelength there. And time determines not just that oscillation rate, but where in the cycle you are, and the cycle is called your period, right, the full cycle, and where you are is the phase. Right? So here, this shows like a waveform, and it's in different phases here, right? So they're offset, it's all the same waveform, but it's offset horizontally for, where the start point is. One full cycle of said oscillation is called a period, right? So you have a period there, and that gets a little bit more important later. So let's make a sine wave. Drop the bass. So that's really all there is to it, right? If you have a method and it takes the frequency, gain, phase, and your time offset there, you do your sine, your math sine function. It's double pi times the frequency times the time in samples plus your phase, and then you're going to multiply it by your gain. And what the gain is it's a multiplier, and it makes it louder or softer. It's essentially like your volume for each part. When you look at the wave on the left, right, that's just hanging out, and then somebody's like, turn it up, and it kind of scales it vertically. That's your gain. So next, let's look at how you do a square wave, because there's not a fun math function for that built in. Again, if we look at this, right, it kind of just hops between like the lower extreme and the higher extreme, right? So we look at this function right here. We have the frequency, gain, and time. FBT is full period time, right? So 1 divided by the frequency is the time that it takes for the entire wave to oscillate, right, for the one time. Half period time is reasonably self-explanatory. And local time is where you're at right now. So what we're returning is we're saying if the local time is less than half period time, if you're less than halfway through your period, right? You're going to be up here, and then if the inverse is the case, you're going to be down here. And then you have cool British drum and bass music. Then for the Skrillex stuff here, you have a very similar thing, except you're dividing the local time by the full period time. And then, it's just dubstep. So here's a crazy one. So say you generate some of these, right? How can you combine them together to make a new sound? This is something that I thought about for a really long time, and I was kind of scared about like how this is going to work out. And then I asked somebody like how that works, and they were like, you literally add them together, right? So if you have this like array of like numbers that represent like a wave and like a signal, and then you have like another array, what do? You just iterate through them and literally add the numbers together. I'm like, you kidding me, right? And they're like, no, that's how it works, man. I'm like, okay. So I go and write the function, and it's like the two waves together, and I'm like, holy shit. Like, addition is a mixing board. That blew my mind. That's how sound gets combined, which is crazy. You just literally add them together. So that greatly simplified the creation process. Right. So now that we have these tones, right? It's just playing. It's like doo, which is all right. But if you want to have individual notes on a rhythm, right, which make up like a sound, how does that work? And that's a thing called an envelope. Right? And what the envelope does is it changes the amplitude or volume of your signal over time. Right? So over a period of time, it's going to for my animation folks in the house, it's going to tween that thing. Right? There's typically 4 stages to an envelope. You have your attack, right, which is your initial ramp up of amplitude here, this little up ramp, and you do that after a note on, right? So a lot of sounds that you're going to hear, they're not going to have much attack, right? They're just going to go for it, just like. But if you're like ambient electronica and you want to be like, right, like that would be your attack. Now, like after that runs its course, there's an initial step down, and that's your decay. And then say you're still holding on to your key on the keyboard, right? That's the sustain. That's where this volume is going to stay while you're holding it. And then your release, you take your finger off of the key, right? That's the time that it takes to zero out, right? So like if you're like, boop, boop. Well, that was a little pitch too. That was not genuine, but you see where I'm going with it. So if we want to make that, right, if we want to shape our sounds, right, we do that with a state machine. Which is great in Reason. So we can go and do this stage variant, right? So we have off, attack, decay, sustain, and release. And then this gross C of mutable, because I'm not a good programmer. So you define what the actual envelope is, right? So we have our minimum level, our current stage, our current level, our multiplier, the current sample that we're on, and the next stage sample index. All right, so this is a pretty heady check piece of code that I'm about to show here. After this. So this creates it with like our defaults here, right? And then here is the actual implementation of an envelope. I don't know if that looks pretty decent size. Can everybody read that? Yeah, okay. It's not like I could zoom it up anyway, but apologize. So over here we have this enter stage method, right? And this is where you would call this if you did like a key down, right? You're going to enter the attack stage. So what you're saying here is the current stage is equal to the next stage that you've passed, and the current sample index is 0, right? So based upon time, we're at 0 right now. And the next stage sample index, what you're saying is, we have the stage order, we have the next stage, we're going to find the index of what the next one's going to be, and then we're going to say how much time needs to elapse before we're going to enter that next stage, before we go from attack to sustain or decay, release, etc. So then we do a little pattern match here on next stage, and this is going to be what actually takes place during these stages, right? So off, right, our current level is 0, so you're saying like make this sound not play at all, and our multiplier is 1.0. For attack here, we set the current level to the minimum level, which is as quiet as it can be, and then we're going to calculate our multiplier to go from super duper quiet to normal volume. Our decay, I'll just So for our decay, right, we're gonna step down a little here. Sustain in my envelope here is kind of a no-op because we don't have a keyboard in play. And then release, right, we're gonna take the current level and step down to the minimum level. All right, so that's how you traverse through these stages of enveloping. And then in the course of our data generation, like where we were applying the gain prior to our sine wave that we created, we're going to be able to call next sample on this envelope, which says like, hey, for the given sample that we're at, what should this volume multiplier be? So we can go through here. Off and sustain are kind of no-ops. Other than that, we're saying if the current sample that we're on, the time has elapsed, is equal to what the next one's going to be, just hop over to the next stage, right? Otherwise, our current level is going to be our current level times our multiplier, right? Our multiplier is defined when we enter the stage, so, you know, it's going to be like a downward multiplier if we're on release, an upward one if we're on attack. And we're going to increment our sample index, and then regardless of that, we're going to return our current level, which will be the volume multiplier that you want to do on your sound. So again, right, we go up at the attack, the decay, the sustain, and the release. Yeah, that's how you can make things sound like pianos or harps or sick bass lines or whatever you want. Envelopes are typically triggered by like MIDI, which is a musical instrument digital interface. It's like a keyboard, or a sequencer. Right? And it would have been cool to bring a MIDI keyboard up here and really jam out. But I don't have port MIDI bindings and I'm not smart enough to write them. So I built a sequencer instead. And I call it the Reason Composer ML808. If you missed that transition, I'm just going to play that back because that should be sweet. Bam! Right? So, one more time. So, what a step sequencer is, if you've ever made beats, you probably know what this is. If you haven't made beats, you might be able to deduce what this does, but I'm just going to explain it anyway. So this lets you create like drum patterns. And like right over here, we have the tempo, right? This can be like the kind of speed of your music, which is in beats per minute. 90 beats per minute is like modern rap BPM. Well, no, I mean, if you're doing like trap music, that's like $1.40, but I digress. And what a beat is, in a typical like 4/4 time signature is going to be a quarter note, right? Which is represented by, each of these like 4 tick regions here. And each one of the individual ones is a step, which is a 16th note. So a beat is like, whereas like a 16th note is like, I mean, depending on the speed that you're moving at, but that's the granularity that we're working with. And here you can turn these on and off, and what they'll do is, throughout time, as you're looping through that time period, they're going to play the individual sounds where you've indicated you want them to play in the course of the loop, right? So, let's talk about sequencing sounds real quick. We'll just hop through some code for a hot, filthy second. So let's say we have this array of zeros and ones. 0 is off, 1 is on. So this should just kind of play like you didn't know this was going to be a beatboxing talk, did you? So you have your current sample. And here we do some calculations to find out, based upon the tempo, how many samples is a step, right? So an individual step, what unit is that? Then here you can get the modulo of your current sample versus the step, and if that's 0, then we know that we're on one of the steps. Then here we can grab the actual index of the step that we're on. So we're gonna say, hey, we're on step 4. Then down here we say like, if in steps here, the specific one that we're on is equal to 1, then we say envelope, enter stage, env, attack, which is a fancy way of saying play it. And then down here, right, we just, if it's greater than 16, right, if we've gone over our loop, reset back to 0, so it just keeps looping. Right? So here's fun stuff, and that's effects. So let's talk about how to make a bit crusher. If you don't know what a bit crusher is, right, it's a combination of adjusting bit depth and downsampling a signal The bit depth is kind of like the resolution of your waves, and downsampling is artificially reducing the sample rate, right? We're at like 44/100 right now, but we can reduce that down. And the idea is it's like a kind of distortion, but it's like this really cool robo distortion, and you can hear it in a little bit. Right, so there's like kind of bit depth. Downsampling is like you take fewer snapshots of the waveform, so to say. Am I doing on time here? Yeah, so here, right, we can create this bit crusher. We can, get our data here, times it by the gain. And then what's really cool is you can just kind of pipe it into this bit crush process method here, right? If we're going to create a bit crusher, right, we're going to get our bit depth, our downsampling, our last sample, and the counter, right, which is like all the other stuff. We're kind of keeping track of where we are. So this is how you do bit crushing. And I'm going to be completely honest with you, I can't explain this to you. This is some algorithm that I pulled out somewhere, and I'm just not smart enough. But I can tell you how downsampling works, which is pretty cool. So we're over here, and we have our counter, and if the counter is less than the downsampling, so we're saying like, if we're downsampling to this amount, if we're not there yet, right, just send in like this cached version here of it. So otherwise, kind of update it, right? So you're saying like, if you're downsampling me here, like every 30 or so, right? You send the last one for 30 frames, and then you update it, and that's not super wild. The other effect that I wanted to talk about was a delay, and a delay is really just an echo, which was kind of wild for me to implement because I don't usually have to do this heavy of programming. Here, right, we can just slap this delay on after the bit crusher, and it's kind of cool because now, like, I can sit here with pipe operators and create a signal chain, which is a lot more fun than any other signal chain that I've ever worked with. So here, right, we have our duration, which is going to be like the time it's going to take for the echo to start. We're going to have our gain, which is going to be like the volume of the echo. We have a delay buffer, so we have to create a parallel buffer to our current buffer, and that's where we're going to store that delay. We can go through, we can create it, right? I create this array here where we're going to store our stuff adjacent to the current buffer. And it's a special buffer because it's a circular buffer, right? A lot of the time, if we had the same array and we just copied it over, there'd be no echo. But if we're going to copy it at a point in the future, right, inevitably we're going to go further over the back of that array, so we're going to have to loop back around and put it in the beginning, and it becomes this circular process. So here's what this looks like. We find out what the max size of that buffer should be based upon how much echo you want to allow people to do. If we're at the end of the sample count, we reset to 0. So here we're going to find out our delay index and our insert index. So this is saying like if I want to delay 0.02 seconds, the point in my buffer where I'm going to start inserting the current signal, that's our insert index. So if it's less than the max, you're just good to go. Otherwise, your insert index is the modulo, which is the right thing. So you're going to loop back around and tack that on the beginning, offset by how much you've overrun the current array. And then applying an echo is really just saying your current input plus the current sample of the delay buffer times the delay gain, and then you just increment your current sample, and your output is an echo delayed signal, which is a fun way to make an echo. All right, so enough of the nerd math stuff. You guys want to see this thing? Woo! Woo! All right. So that was kind of like the audio portion, but I want to actually talk a little bit about building this. So I'm also going to pop open Visual Studio Code for a moment. I was kind of worried. I'm like, what's going to pop up? Like, what could I possibly be working on in Visual Studio Code that wouldn't be appropriate? I don't know. It's possible. All right, so here's my app. It's called Camel Synth. Watch how fast this thing starts up. It's out of control. Do you see that? Whoa! Everybody say thanks, Brian. Yeah, so this is written, just a little technical breakdown on this thing. Again, right, all the audio stuff, this is 100% native Reason. And this is the first time I've ever done an app that was 100% native Reason. I did like a Reason React or React Native thing before, and that was cool. That was dope, no doubt. But it was still JavaScript interpretation or what have you. This is completely native. And I've built my fair share of Electron apps, which I think like the Hello World clocks in at like 112 megabytes or something like that, right? To get words on a screen. This thing is like 2 megabytes with assets. It's bananas. Yeah. Clap for me. Clap for yourselves. I just made a drum machine. Yeah. So I guess everybody wants to hear this thing, right? So they're all synthesized, all the sounds, right? There's no samples. A lot of time when you do drums, they'll have like drum samples, but all these sounds are made out of those cool signal math functions that I was showing you before, and I'll show you how. So I'll just show you some of these features here for a second before we really get into it. We have kick, snare, hat, cowbell, you can't get enough of that, and a clav. And they sequence over here. So I could take the clav out. All right. So let's just like double time it. Really should have done like a hold thing for that. All right. So now I can come here and we can make like some trap music. So then you can come down here, right? We have like all these things, like the tone, like the snare right now. Make it tighter. Whoa, hey now. There's not really that much bass on this thing, but if there was, this would be like. And then, remember I was telling you about that robo distortion? The big crusher? Check this out. Glitch mob. And then you come in, the delay, the echo, the circular buffer, right? Well, that's that. I need to make it tighter. You do all that stuff. And then low pass filter, right? We're in the club basement, you know what I'm talking about? This is like when Drake is saying something cool. But yeah, that's like the long and short of the functionality there for this thing. So the wildest part about this is, not only is the audio native, not only is the audio just a bunch of numbers getting thrown at a sound card, but the whole UI is native via Reverie. And you saw Brian talking about Reverie before. It's amazing. And I'm not some native UI guy. I'm a JavaScript front-end engineer. And this was not super hard to put together. And I'll show you. Hey now. Yeah, this is regular Reverie. So if you're used to writing React apps on the web, or even React Native apps, because the primitives are a little bit closer to that, this is not that much of a stretch at all. You already know how to do this, right? You come here. This is very, very familiar looking code, right? We look here at like all the buttons and stuff like that. Like, this is regular UI, just like you would do on the web, except it doesn't jank out or behave weirdly. It just works. Who said that? Yeah, so just outside of the UI, right, to dive in a little bit more closely about how you go from like math.sign to like Young Thug. We'll take a look at the app state, which is pretty thorough. I think I have like 6 minutes left or something like that, so I think we make some pretty good progress in here. So the baseline app state, right, so we have playing, right, is this thing playing? We have our tempo, we have the active step, and that's kind of there just to track which one of these should be lit up. If you watch it play, like it'll light them up as it's on the one that it's gonna play. All right, so that's like your active step. And we have the tracks, right, and there's 5 tracks. Each one of the tracks is kind of hard-coded to one of these sounds here. And then we have the master effect enabled, and then the master effects right here and all their stuff. So let's take a look at track real quick, because this is where a lot of like the actual drum synthesis magic happens. We have our steps, right? And that's like if you click between these, you're going to see different ones have different arrangements. That's where that gets stored. And then we have osc, right, which is an array of oscillators that'll make up what that sound is, right? And then we have a variety of these things: the frequency, gain, attack, decay, sustain, release, all the envelope stuff that we can modify down here. And if you have the snare, you want to make it loud. Right, I'm on the snare. You do all that fun stuff. So let's hop down to a track. Right, these are all just the stuff that lets you update things from the UI. It's not super important. We can hop down to these tracks, and you get to see how some of this works. Right. So the first one's a kick. It's an okay kick. If you're making like 808 rap music, like right, it's a sine wave, and that's really all there is to it. Which is cool. I don't know why this keeps selecting the whole thing. It's driving me nuts. Down here, though, right, here's our first combined one. And this is a snare drum, right? So when you're synthesizing these drums, you want to say, how do you make these drums? Right? So you say, okay, snare drum. So it's a drum, right? So we're going to want like a sine, right? So it's going to be like, boop, and that's your drum. But then a snare drum has a bunch of little metal cords on the bottom of it strapped across it, so it goes, right? So how do we do that, right? And that's with a noise wave. And a noise is just, it's like throwing math.random with a constraint on -1 to +1. And what that gives you is literally that exact sound. But it's super helpful with like the guy from like Police Academy. But it gives you that, right? So if you combine these two, right, and then you put a low pass filter on them, and you know, with these settings right here, you listen, and it's right. That's what a snare drum is. So you combine those things, and then you get it. What's particularly interesting was the hi-hat. So I thought with a hi-hat, like right, you could just make that out of the noise, right? You take a little slice of the noise, but it didn't sound right. So I went and looked at how the actual TR-808 did hi-hats, right? So if we take the rest of this out of here, and we just listen to the hi-hat for a second, it's got a pretty unique character to it. If we just put it on the eighth notes here, right? Right? It's kind of wild. And the way that you actually do that is a series of square waves, right, with like weirdly tonal offsets. And all of those together give you this sound that is a hi-hat, right? And then you just put a high-pass filter on it and you get a hi-hat. That was kind of wild. I have 2 minutes left. Hopefully we can make it through the other two. Arguably the most important sound of any drum machine outside of a clap, which I don't have, is your cowbell. It's so crucial to have a cowbell if you want to earn the respect of your peers. You know, you want to, all right? And the way you do that, right, is by combining the square and the saw and then doing a pitch offset. So this one is offset up to 6.0, this one's offset to 4, so it creates like this little mini like triad chord. Well, it's not really a triad, but it's like a, yeah. You know, just with the envelope, and there you have it. There's a cowbell. Yeah, and you know, outside of that, the whole rest of this is just a bunch of super boring plumbing. If we look at the audio.re, you know, it's all the stuff that I was showing about how to write stuff to port audio, filling our stream. Of course, we have tracks, so the way that I'm doing it is I take the tracks and do a fold left with them, and then inside of them, I fold the oscillators that are within the track. And we apply the envelopes, we apply the filters, but really it's just squashing everything together and adding all the numbers together where they belong, and then doing this super dope pipe through all the effects if they're enabled. Yeah, this is the same exact code that I had in the slide for filling your buffer array. So I think I'm out of time, but if you want to play with this, it's on GitHub, it's open source. Also on GitHub is the executable if you want to install it and play with it at home. And if you want to know anything more about it outside of that, I'll be around all day. Hit me up. Thank you.